name is Xiaowei. I work on AnyScale machine learning team. Today, the topic of my talk is RayTune, distributed hyperparameter optimization made simple. So actually, I just recently joined AnyScale as a software engineer for 2 months. So I'm super pumped today to present some of the best work done by my team and my coworkers. At the same time, I'm also a little nervous as Ray and RayTune is such a vast and big topic to talk about, and there are so many things to learn. But hopefully, I can bring something new and fresh to the field, and you can finish the talk with some knowledge about the framework and library that you can incorporate into your system and make your workflow easier. OK, this is the agenda for today. First, we're going to go through some background on Ray and RayTune, as well as some challenges in hyperparameter optimization, also known as HPO. Next, we're going to go through some cutting-edge HPO algorithms offered by RayTune. And we're also going to go through how RayTune does distributed HPO. And next, we're going to look at how RayTune fits nicely into the whole machine learning ecosystem by looking at a tune-sklearn example. We're also going to show some Python code as well as a short demo to showcase the concept. So stay tuned. OK, so what is Ray? This is a question I've been pondering over and over again through my interview process and my onboarding process. So simply put, Ray is a simple and universal framework for distributed computing. It's first developed at Berkeley Rice Lab, and it's open sourced. It's mostly Python. And AnyScale is the company that's sitting behind Ray, looking at how to commercialize it. Over the years, Ray has really come a long way. In fact, there are over 500 users and contributors from a huge number of companies. For example, Ant Group is deploying over 200K cores over Ray for applications like recommendation system, fraud detection, and online learning. On the other hand, Amazon is using Ray to improve their data processing throughput to over 1 petabyte per hour, while decreasing their cost by 90%. Ray can be run anywhere, from public cloud to on-premise cloud to Kubernetes, as well as just your laptop. It provides a generic and low-level distributed programming APIs so that distributed applications can be built on top of it. So I think Jules also mentioned this. So let's maybe look at some code examples. So as programmers, we're familiar with functions and classes. And Ray in the distributed world maps it to tasks and actors. Let's say I have defined my function, which is a normal function that can run locally. By simply apply a ray.remote decorator on top of this function, we can translate it into a Ray task. And by invoking this function by myfunction.remote, this will immediately return an object reference, also known as a future. And then it will create a task that will be executed on the worker process. The result can later be retrieved using ray.get over this object reference. So one can easily see that this kind of API can make parallel programming a lot easier. So let's look at a slow function that may take some time to execute. We can still decorate it with ray.remote to translate it into a task. And one can easily launch a group of these slow functions to execute in parallel. And one can easily wait for the result using ray.get and feeding in a list of futures. OK, so given this kind of distributed programming APIs, let's look at how does it supply all kinds of distributed applications on top of Ray. One thing I noticed that is really unique about Ray is Ray can build an end-to-end distributed platform. For example, in the context of machine learning, we can build featureization, hyperparameter tuning, training, and model serving all on Ray. So to really boost the adoption of Ray ecosystem, the Ray team actually writes a few first-party native Ray libraries on top of Ray. For example, the topic of today, which is RayTune, is one such library that specializes in hyperparameter tuning. And RaySGD is another library that specializes in distributed training, so on and so forth. So one observation I had about Ray is sometimes the success of one such library can really drive our users and customers to bring other components of their systems onto Ray as well. So the Ray ecosystem can be really sticky. Okay, so having talked about Ray, so what is RayTune? RayTune is the hyperparameter optimization library that sits on top of Ray that leverages all these distributed programming APIs supplied by Ray. So here, I want to show a benchmark done by the Uber team that is showcasing how they compare Ray against their current production tuning system. And the result shows that RayTune brings a 2x efficiency improvement in terms of machine hours. So one may start to wonder, how is that efficiency gain possible? RayTune achieves that by providing efficient cutting-edge HPO algorithms, as well as distributing and coordinating parallel trials in a fault-tolerant and elastic manner. So these two are the two fundamental pillars of RayTune that we're going to deep dive later in the talk. And all in all, RayTune can save your time and cost every step of hyperparameter optimization. So let's maybe first set some terminology straight. So hyperparameters are defined in the context of model parameters. So as you may know, model parameters are learned during training, while hyperparameters are set before training. So some examples of hyperparameters include model type and architecture. For example, in this case of convolutional neural network, so the number of layers and the structure of each layer are all hyperparameters. Basically, every number you see in this picture is a hyperparameter. Hyperparameter also include learning and training related parameters like learning rate and batch size are the two most important ones. It also includes pipeline configurations as well. For example, in this case, we may have an XGBoost classifier, which can easily have 6 to 10 hyperparameters to tune. But when we put it in the whole machine learning pipeline, we can easily have another few hyperparameters from the configurations of imputer, for example, categorical encoder, under and over sampler. So we can easily have maybe 15 hyperparameters to tune. So this leads to what are the current challenges in hyperparameter optimization. So of course, it's time-consuming because, as we have shown, there are a large number of combinations to try out. And this is a black box optimization in the sense that the evaluation of each combination, also known as trial, involves model training, which can take days and weeks. And of course, resources are expensive, especially when you consider GPUs and TPUs. So this is where RayTune comes into the picture. So RayTune has offered efficient algorithms that can enable running trials in parallel. It also offers effective orchestration of distributed trials. So basically, minimal change is involved to change a tuning job that from running on a single process on the laptop to running on a multi-node, multi-GPU cluster. And all of these are offered to our user with very easy-to-use APIs. OK, so next, we're going to go over some HPO algorithms, hyperparameter algorithms offered by RayTune. So this will include some of the classical ones, like exhaustive search, but also include some of the more advanced ones, like advanced scheduling. So please bear with me if this section can be a little algorithmic heavy. But if there's one message I want to convey during this section is RayTune has over 15 algorithms natively provided or integrated in the library, and one can easily swap out different algorithms with very minimal code change. OK, so let's start. So the first category I want to talk about is exhaustive search. I think this is probably most familiar one for most people. So there are two kinds of searching algorithm here. One is grid search, and the other is random search. So let's first look at grid search. So in grid search, which is the left picture here. So for grid search, in this case, we have two hyperparameters. And for each hyperparameter, we have 3 discrete values to choose from. So altogether, we have 9 combinations or 9 trials to try out. So and here there's a curve showing the objective function, which can be also like loss function in this case. So the optimal trial should be the trial that has the lowest score here, which is about this point. So as you can see that by defining this discrete search space, we can easily miss out the optimal point, which is less favorable. We also spend a lot of computing cycles to try out trials along this direction, which is unimportant. So random search is very similar to grid search, except that for random search, each hyperparameter can have a distribution to randomly choose values from. So I think both of these algorithms are easy to implement, and they can be easily parallelizable. But the problem with them is they are not very efficient, especially when search space is huge and we have a lot of hyperparameters to tune, as we have seen in previous slides. So given that exhaustive search is not that efficient, there comes the Bayesian optimization. So Bayesian optimization is based on this very simple intuition. That is, what if we can use the results from previous combinations or previous trials to decide what is the next trial to try, so that we can maximize the probability to find a trial that can outperform all the previous ones. So to be consistent, I still use a 2-dimensional search space here. So you can see the contour plot here shows the objective function. The blue area corresponds to a smaller loss function than the red area. So you can see instead of uniformly or randomly distribute trials in this search space, actually the trials are more concentrated towards the blue area, which is the more optimal area. This is a more preferred behavior so that we can find the best trial in less time or resources. Of course, there's a problem with Bayesian optimization as well, because as you can see, it's inherently sequential in the sense that you really need to use the results from previous trials so that to decide what is the next one to try. There are several popular libraries in this for Bayesian optimization, including HyperOpt and Optuna, both of which are integrated into RayTune. Okay, so we know the problem with Bayesian optimization is it's inherently sequential, but modern and more advanced hyperparameter optimization algorithms are mostly focusing on parallel computing. So this is where advanced scheduling is coming into picture. So one type in the advanced scheduling category is called early stopping. So early stopping is so it works like this. So we first found out a lot of parallel trials during the initial exploration phase. And then in the middle, we use intermediate results to prune underperforming trials and save time and computing resources. Here is a simple illustration of this concept. So this figure shows how different trials progress over time. So the x-axis is the training time. The y-axis is the validation metric, which basically measures how good each trial performs by far. So, and a different color represents different trials. So as you can see, at first we launched a lot of trials, but at some intermediate point, we check their results, and we stop the underperforming ones, and we only allow the top performing ones to proceed. In this way, we can save the resources and reallocate the resources to more promising trials or to search the search space more. So in this category, there are also some famous algorithms, including median stopping, ASHA, and hyperband, all of which are part of RayTune as well. And another good news is this type of early stopping can be combined with Bayesian optimization, so we sort of get the best from both worlds. Another one I want to quickly mention is called population-based training. This is an evolutionary algorithm, mostly used in deep learning. So the idea is similar to early stopping. So it also starts to evaluate a population in parallel, and every trial also has a performance or score associated with them. And in the middle, we'll start to compare how trials perform, and we'll terminate lowest performers. And we'll copy over weights of the better performers over and mutate the weights a little bit and proceed with our training. Okay, hopefully I haven't lost you in all these algorithmic details yet. So let's review what we have talked so far. So there are various HPO algorithms with a trend of going parallel. And more advanced HPO algorithms are often hard to implement. And this is even more true in a distributed setting. Okay, the good news is Raytune implements and integrates with all the algorithms that we have so far talked about, and it allows users to swap out different algorithms really, really easily. And why do we spend time to go over these algorithms? I think one point I really want to make is we want to understand what are some of the architecture requirements imposed by these algorithms and what kind of system we need to build in order to support all these algorithms so that we can support efficient HPO. So one thing we notice is all these algorithms require granular control over when to start, when to pause, early stop, restore, or even mutate a trial at specific iterations with very little overhead. It also requires a master worker sort of architecture that centralizes decision-making process. And of course, as with any distributed system, we want elasticity and fault tolerance. So Raytune is such a system for distributed HPO. So let's maybe put it into the context with some code example. So let's say we define a training function that takes in some kind of hyperparameter configuration here. We also define a model, which is a convolutional neural network in this case. We run through a range of epochs. And at the end of each epoch, we will calculate the current loss of the trial, and we will report that through the tune-report API. So this training function is everything Raytune needs to know about how to carry a single trial. And then we further call tune.run with this training function, and we define a hyperparameter search space, which in this case is just very simple alpha parameter, which is a uniform distribution here. And we want to run 100 trials. And for the scheduler, we choose Asha, which you may still remember is a type of early stopping scheduling mechanism. And for the search algorithm, we choose Optuna, which is a kind of Bayesian optimization. So how does this map into the architecture? So let's say we have a head node, and it runs a driver process that orchestrates the tune run. And the orchestrator also has the HPO algorithm running. So based on the result from the HPO algorithm, as well as the available resources in the cluster, the orchestrator may decide how many trials to launch. And you may still recall from the race section, we talk about remote actors. So each trial is launched into a remote actor and runs there. And at the end of each epoch, you may still remember we report metrics back to the orchestrator. And the orchestrator, based on all the reported metrics, will decide what are the trials to continue to run and what are the trials to early stop or do something else. So for example, we early stop this trial. And then the resources are freed up, and then it can be repurposed to explore some new trials. So in this case, the orchestrator decides to place a new trial on top of this actor. Just as in any other distributed system, the nodes may go down, the process may crash, so we need a mechanism to persist intermediate states. So we call this process checkpointing process. So the intermediate states of trials are automatically checkpointed by some configuration to cloud storage. So let's say a worker process goes down. And orchestrator will then place a new, so a new actor will come up fresh, and then the orchestrator will then put the crashed trial on top of this actor with the loaded checkpoint from remote cloud storage. Okay, let's review what we have talked about so far. So what makes RayTune so special is it provides efficient HPO algorithms, and it distributes and coordinates parallel trials in a fault-tolerant and elastic manner. And also, it's deeply integrated with the whole machine learning ecosystem. So how many of you have used scikit-learn? Yes, I've seen so many hands. I also love scikit-learn for its simple and easy-to-use APIs. So what if I'm a scikit-learn user, I use scikit-learn for HPO, but I also want to potentially leverage RayTune for hyperparameter optimization for its advanced algorithms as well as distributed offering. So the good news is tune-sklearn is built exactly for that. It's a scikit-learn-wrapper for RayTune. It's a drop-in replacement for scikit-learn model selection module. It provides a familiar and simple-to-use API for advanced and more and distributed HPO. So you can check out the link here. So let me quickly show what do I mean by drop-in replacement. So this is a scikit-learn a code snippet. So notice here the n jobs is -1. This just means we can use all the cores on this single machine. And by drop-in replacement, we can just change 2 lines of code to change it to use tune-sklearn, which is using RayTune underneath. And n jobs equals to -1 here means we can use all the resources throughout the entire cluster. So we are not limited to a single machine anymore. Okay, so lastly, I want to quickly showcase a demo that further illustrate our concept of this drop-in replacement. So this is a driver safety prediction. This problem and data set is adapted from a Kaggle problem. Before the demo, I already started a cluster through the Ray cluster launcher. So altogether, I have 5 nodes, and each node has 8 CPUs. For simplicity, I use Jupyter Notebook that runs on a head node. Okay, let's look at this demo. So let's first look at the data set size. It's a pretty big data set. It's a realistic problem. And then we define some XGBoost classifier. By calling ray.init, we can attach to the already running Ray cluster. It's a little slow. Yes. So we can then inspect the Ray cluster resources, especially the CPU number here. So like we said, we have 5 nodes, and each node has 8 CPUs. So altogether, we have 40 CPUs. And then let's first write some code to run a hyperparameter optimization using the native scikit-learn API. And this is how it looks like. And for the sake of time, I just stop it. And then let's look at how do we do drop-in replacement to change it to use RayTune, which is quite straightforward. Yeah, the network is a little slow. Sorry, the network is very slow here. And here we launch a tune search CV. And we have a progress bar to show the progress here. Let me. Sorry. And I just want to quickly show the final result. So final result we can see from the search CV, the experimental analysis object. So in this case, we can show how the cross-validation score changes over time, because it improves over time because we discover and finish new trials that has better performance. So this concludes my demo. Thank you.